Welcome to this explainer on simple probability. Look, if you're a Form 2 student tackling the KSM syllabus, or maybe just someone who feels like probability is a bunch of abstract guesswork, you are in the exact right place. Today, we're going to transform those abstract concepts into rock-solid certainty. By the end of this, you'll literally have the tools to measure the likelihood of any event. Let's get right into it.
Here's our roadmap for today. We'll start with a quick introduction, move into experiment versus theory, and then look at sample spaces. After that, we'll tackle the complement of an event, put it all into action with some problem solving, and wrap up with a summary of your key formulas.
All right, Section 1, Introduction to Probability.
At its absolute core, probability is just the exact measurement of how likely an event is to actually happen. And the golden rule? This measurement always lives strictly between 0 and 1. You'll see it as a fraction, maybe 1/2, a decimal like 0.5, or a percentage like 50%. 0, that means an event is completely impossible. No way it's happening. And a 1 means it is absolutely certain. It's a sure thing.
Moving on to Section 2, Experiment versus Theory, Testing Reality.
So, let's define experimental probability. It's exactly what it sounds like. Probability you get directly from conducting an actual experiment. You calculate it by taking the frequency of an event, meaning how many times it actually happened, and dividing it by the total number of trials. Imagine you're tossing a coin. Theoretically, sure, you'd expect heads 50% of the time, but actually tracking the results in an experiment, that gives you reality.
And what's really fascinating here is the reality check. A student named Sunil tossed a coin 20 times, and he landed on heads 13 times. That is a 65% experimental probability, which is way higher than our 50% theoretical expectation, right? But watch what happens when he increases his trials to 50 tosses. He gets 26 heads, and boom, the experimental probability drops to 52%. As he increased the trials, his actual real-world outcome got so much closer to that theoretical expectation. It's like math correcting itself in real time.
Okay, Section 3, Sample Spaces, Possible Outcomes.
First up, we need to define our terms. The sample space, which we denote with a big capital S, is basically our entire universe of all possible outcomes for any given experiment. And we use this notation, lowercase n, bracket s, which we read as n of s to represent the exact number of elements inside that universe.
Let's look at a concrete example to make this stick. Suppose an experiment asks us to randomly choose a prime number between 20 and 40. Well, if we list out our sample space, our S, we find exactly 4 prime numbers: 23, 29, 31, and 37. So because there are exactly 4 specific outcomes in this set, our n of S simply equals 4. Super straightforward.
Now we can also visualize this whole thing using a tree diagram. Honestly, this is an incredible tool for tracking multiple steps. Imagine you're at the school cooperative. Step 1, you pick a brand P pencil. Step 2, you grab an eraser. And your choices are red, green, blue, or yellow. By following the branches of our tree, we clearly see exactly 4 possible paired outcomes. So once again, our sample space size, our n of s, is 4.
And here it is, the absolute master formula for the probability of an event, which we'll just call event A. To find the probability, or P of A, we simply take n of A, which is the number of ways our specific event can actually happen, and we divide it by n of S, our total number of possible outcomes in the sample space.
Let's apply this master formula visually. Picture a box holding 25 green apples and 35 red apples. That gives us a total sample space, our n of s, of 60 apples. Now, if we want to calculate the probability of blindly picking a green apple, our n of a is 25. So we place 25 over 60. And when we simplify that fraction, we arrive at a perfectly reduced probability of 5 over 12. See? Not so bad.
All right, Section 4, Complement of an Event, the flip side.
So the crucial point here is that a complement, which we write mathematically as A prime using a little apostrophe, is simply everything in our universal sample space that is not our target event. Think of it this way. If event A is what we want, A prime is literally everything else. It's the leftovers. Check this out. If we take the integers 1 through 20 and we define event A as choosing a prime number, well, we find exactly 8 prime numbers. Therefore, event A prime, our complement, is simply the 12 non-prime numbers that are left over. Together, they make up the entire 20-number universe of our sample space.
And this brilliantly illustrates the golden rule of complements. The probability of an event
plus the probability of its complement absolutely always adds up to a perfect 1. P of A plus P of A prime equals 1, and because of this, we can quickly calculate the complement by just subtracting our event's probability from 1. Let me tell you, this is a massive shortcut for solving complex problems on exams.
Section 5. Problem solving. In action. Time to put all these pieces together.
Imagine for a second you're a shirt manufacturer. You need to manage some specific numbers to calculate your future business success. So in 1 month, you produce 80 shirts. You consistently sell 15 shirts per week, and your profit for every single batch of 15 sold is exactly RM 135. Let's break down the probabilities here.
First, we need to find the probability of your shirts actually being sold in a single month. Since there are roughly 4 weeks in a month, selling 15 shirts a week means you sell 60 shirts in total. Using our master formula, we take the 60 shirts sold over the 80 shirts produced. That gives us 60 over 80, which simplifies beautifully down to a 3/4 probability of a sale.
Next, let's project this out. What is your profit going to be for 2 months? We just applied that 3/4 probability to 2 months of production. 3/4 of 80 shirts is 60, and multiplied by 2 months, that gives us 120 sold shirts. Since you make RM 135 for every 15 shirts, we just divide 120 by 15, which gives us 8 batches. 8 batches times RM 135 yields a highly accurate calculated total profit of RM 1080. Finally, what about the inventory that doesn't sell? This is exactly where our handy complement formula comes in to save the day. If the probability of selling a shirt is 3/4, then the probability of a shirt remaining unsold is 1 minus 3/4. That leaves a 1/4 probability. Multiply that 1/4 by the 80 pieces produced, and it translates to exactly 20 unsold pieces in a month. Just like that, probability helps you perfectly manage your inventory.
Let's wrap this up. Section 6. Summary and Formulas Key Takeaways.
Here is your final revision checklist, so walk this in. Probability must sit between 0 and 1. Memorize your master formula. P of A equals N of A over N of S. Remember the complement rule. P of A prime equals 1 minus P of A. And finally, my biggest tip for you, always simplify your fractions down to their lowest terms and scan your test questions carefully for the word not. That word is your instant flashing light clue to use the complement formula.
You now possess the mathematical toolkit to look at the randomness of the world and actually measure it with exact certainty. From coin tosses to business profits, the numbers are just there waiting for you. So now that you have these formulas, how will you use simple probability to predict the certainty of your next big outcome? Keep analyzing, keep calculating, and thanks for joining me on this explainer.